Hello, welcome to Combined Magnetic and Electric Fields, also including mass spectrometers. So when we combine magnetic and electric fields, some interesting things can happen. And we just have to recall what we know about electric fields and what we recall about magnetic fields and just put them together. And so usually this is talking about when we have charged particles. And we can have a beam of charged particles entering a region where there's both magnetic and electric fields. Usually they're mutually perpendicular to each other, but we'll see a couple of examples that highlight that. And what you've got to realize is that each charge simultaneously experiences the effects of both. So you have to work out what's going to happen due to the electric field and what's going to happen due to the magnetic field, and both of those things will occur at the same time. So here we have a magnetic field going from left to right. Here's an electric field going down. A positive charge would experience a force due to the magnetic field down, and a force due to the electric field down. So this particle would move that way. Whereas a negative charge is experiencing a force in opposite directions, and therefore these two could theoretically cancel each other out, and we'll see situations where that occurs. Here's another example. All they've done here is swap the electric field around, so it's now the positive charge into the page is experiencing almost equal forces if we've tuned in the magnetic field and the electric field. Now, because we can create magnetic fields and electric fields, we can tune them both in so that those forces are equal. Sort of similar to what we did in the Millikan oil drop experiment, where we balanced gravity and the electric field, and we were able to get the droplets stationary. This is a different scenario, but we can control what happens to these particles. And so a mass spectrometer uses this, and it's called a velocity separator. And so what happens is you have your source in your mass spectrometer. Usually that's just a filament, or it could be something that's boiling off ions. There's a whole variety of ways that we can make charged particles. They then enter this area, and here we've got a magnetic field labelled as B. That little arrow is not a direction, that just tells you sometimes some textbooks have a convention where anything that's a vector has a little arrow above it. And so the velocity here and the magnetic field and the electric field have a little arrow above them. Just means it's a vector quantity. A lot of textbooks don't use that because it's just a bit hard to typeset. So into the page for the magnetic field, and the electric field is going down. Okay, so if this was a positive charge, it would experience a force downwards towards this plate due to the electric field, and it would experience a force upwards if we used our right hand charged particle rule thing. Remembering our thumb is conventional current, which also represents the flow of positive charges, and so I'm pointing here at the screen, and so I can see that the force would be up the page or up the screen here. And remember that the force due to the magnetic field is QVB, whereas the force due to the electric field is QE, and that will give you a constant, that will be balanced for certain velocities, because there's this velocity component here. And if you have a range of velocities coming into the field, if we tweak the electric and magnetic field, we can tweak it so that only a certain velocity comes out, the velocity that corresponds to the balancing magnetic force to the electric force, because there's no V here. And so that's why it's called a velocity selector. All the other velocities are bent off, either towards or away from the plate. And so we have this equation here, which you find on your information sheet, where V is the velocity in meters per second, B would be the electric field, and E is the magnetic field. So if we know either these two, we can work out the velocity that's being selected by it. Alright, and mass spectrometers use that. In this case they've got an electron beam and a So this might be a sample that you've chemically dissolved, you put it onto a filament, it vaporizes it, you get ions, they get accelerated through an electric field, we've done all this, and then they experience a magnetic field and they get separated and sent to the detector plate. And another version of the similar but different things. Okay. And so here's our velocities. Here's another diagram just showing what we can do with them. And this is our velocity selector again. So we've got a magnetic field into the page, an electric field down the page, and so they shoot out here, and all these ions will have the same velocity, and then they enter a second region. So it gets a little bit confusing. A second region where there's only a magnetic field. Now, because they're all travelling at the same velocity, and we've got R equals mv/b, it will be the mass that determines the radius. And so the larger they are, the further they'll get out. So if you have your detector here, you can separate the ions according to their mass. And that's what we do in a mass spectrometer. A very sensitive instrument for doing that. And so here they're separating out ions. Not ions, isotopes, sorry. And this is just another diagram. It all condensed down into a very small thing. So for ions with the same charge, the smaller mass gets a smaller r, assuming that they all come out with the same velocity, and the larger mass gets a larger diameter. For ions with the same mass, the larger the charge, the smaller the radius, because the larger the force. This is as if there's a magnetic field in this case, similar to the last diagram. Okay, so there's our equation that we use. Again, this is the angle of the motion to the magnetic field, and that's always going to be just 1. So we need to know the mass, the velocity, the charge, and the magnetic field strength. We can work out R. So you should now be able to do question 20 in your workbook. And this is just another diagram showing, this is the velocity selector, and then it comes out in this case, and you can check you can use these diagrams to check your rules. And in this case, the magnetic field's coming towards you, so these must all be, let's see, it's experiencing a force. Let me draw this. So these guys are all experiencing a force in that direction towards the center. So this is circular motion, remember. So we're tying in electric fields, magnetic fields, and circular motion all into the one. So this is why sometimes physics can get a little bit confusing. So if I'm saying that the magnetic field's coming out of the page, I'm looking at the screen now. So I would put my hand like this. So these guys, the charges must be positive in this case to get that arrangement. I hope that's right. Let me know if I'm wrong and I'll correct it. Right. What else is happening here? Nothing. So what do mass spectrometers look like? Well, this is one from a few years ago. The mass spectrometer is actually this little thing here going across from here to there. Okay, and this is one that's probably in a science. You can see a diagram there of a mass spectrometer. And all this stuff is, this is a preparation for the ions probably, and these are all the programs that run it. Fairly old, as you can tell from the laptop. So you should also be able to do those questions in your workbook. Now the next video that we're going to look at is on cyclotrons. So that should do us for now. See ya.